Okay, we talked about this equation. That force is the force on a charged particle with charge Q is Q times E. And I talked about how we're taking this transition from talking about electric fields into talking about electric potential when we're moving from, say, chapter 21 and 22 to chapter 23, where we talk about potential. And that's akin to the move in physics 1 from talking about forces to talking about work and energy and things like that. So that's why I wrote these things down here. And then I was talking about how the electric field between two closely spaced, oppositely charged parallel plates is constant. And so that means I can move this way, like, so the electric field here is the same as the electric field here, is the same as the electric field here, right? Moving between these two plates, and also moving up and down between these plates, that the electric field is the same here as there, as there, as there. And the only point at which this assumption breaks down is when you get to these edges here, when it's not near the middle, but very close to the edges. And this phenomenon is called fringing. So fringing. So at the edges of these parallel plates, you'll see the electric field lines start to bow out a little bit, and this phenomenon is called fringing. So that's where the assumption breaks down. Okay, so so this is called a capacitor. Let's go on to the next thing. So you remember when we did a calculation, and just, I forgot to say this, but anybody jump in with questions at any time if you want to ask a question. So you might remember we did this calculation here where we calculated the electric field from a continuous distribution of charge for a charged disk, and then we took the limit, say, as this radius r here goes to infinity, so that we were calculating the electric field a distance z, say, from an infinitely large plane of charge. And I had said, well, you know, when you have when you're really, really close to a plane of charge here, the distance between, if you're at a point, so if you're at point P here, the distance z is really, really, really small compared to capital R, the radius of the disk, then it's almost like being close to an infinite plane, right? If you can think about your shrunk down to the size of an electron, that's like really, really close to a dinner plate, something the size of a dinner plate. Well, if you're like a nanometer away from a dinner plate, that dinner plate is going to appear to be infinite to you, right? In the same way that you can stand, you know, and on flat Earth on a plane, and it looks to you like, you know, a flat plane that goes, the ground will look to you like a flat plane that goes out in every direction, even though it's a sphere, right? Because it's just a question of scale. We had also talked about then how the electric field strength is independent of how far away you are from an infinite plane. The electric field was dependent only on the surface charge density on the plane. So if you have a surface charge density sigma, if sigma is the charge over the area, right, the charge per unit area on a plate of charge, then the electric field was equal to sigma over epsilon naught, sigma over 2 epsilon naught, and that was pointing radially outward. Well, let's use n hat. Say this is pointing radially outward in this direction, normal to the surface of the plate. Okay, so we talked about those things. Now, let's think about a charge that goes into this into a capacitor. Now, here we have an electron accelerated by this external electric field. So I had posted this on Blackboard and sent out an announcement on Friday. So I had solved a problem similar to this. Like, actually, it was a tougher one because it was the particle came in from the side. But I did want to review for you the work energy principle really quickly. So the work energy principle, or the WEP, says that the net work done on an object is equal to the change in the kinetic energy of a particle. So, and work is force dot distance, right, in the case where force is constant, and it will be since the electric field is constant between these two plates. So in that case, in case you wanted to solve this problem where there's this constant electric field, there's electrons starting from rest, and you want to know its final velocity as after it travels a certain distance, that was 10 centimeters, distance here, 10 centimeters, then you could use the WEP, or the work energy principle, if you wanted to use energy considerations. And you could go through this whole calculation here. I'm not going to repeat the entire thing, but remember that work is force dot distance. And so the force and the electric field are in opposite directions, because the force is Q times the electric field. Q is minus E for an electron. And there's this external electric field that exists in here. And you can take this, then calculate the net work done by just taking F dot D, and the distance here would be 10 centimeters, and set this equal to 1/2 mv squared, because that's the change. It starts from rest, so the 1/2 mv final squared minus 1/2 mv initial squared. Okay, and v initial, it starts from rest, so this is equal to 0. And you could use this to get the final speed of the electron using the work energy principle. Okay, so something else that you should note is that there's another way of talking about this. So what you could talk about is, instead of an electric field lines, you could talk about voltages. And you could talk about how the electric field, instead of the electric field inducing a force, you could talk about the voltage at this plate, right? And this would be this would be a low voltage. Another way of saying it is a low electric potential. And this would be a high voltage, or a high electric potential. And then you could use energy considerations to talk about why this thing accelerates. Okay, now voltage V is just defined as U over Q, where U is the potential energy that a charge would have at a specific location. So we talk about electric potential or voltage as just being the potential energy that a charge would have if it was placed at a given point, and then we divide by the charge that point charge has. So the idea here is that you can define a voltage you can define a voltage field, or the value that voltage has at each point in space, and then relate this to energy to figure out how charges move. What I could do then is draw surfaces of electric potential, a constant electric potential. Okay. Note that voltage or electric potential, that this is a scalar field, so there's no arrows on a potential surface, but I could draw lines that have lines of constant electric potential. So there would be higher here and lower there, lower here or there. and that would cause this motion through this voltage. Okay, so at this point in the video, the audio went bad, and so I'm going to do this right now, and I don't have a ton of time, so I'm going to do it really quick, going through the things that we covered when the audio was lost. Okay, so first thing, electron volt is 1.6 times 10 to the negative 19th joules. That might sound familiar to you because it's just the elementary charge of an electron, E, there, times 1 volt, right? And a volt is a joule per coulomb. So there's three different kinds of things I want you to know and keep separate. The first is voltage, or electric potential. Voltage and electric potential are exactly the same thing, so those are the same thing. There are units of voltage. Those are called volts. A volt is a joule per coulomb. So there's voltage, that's a physical quantity, and then there's volts. That's a unit. Okay, kind of confusing, I know. But if you take the elementary charge of an electron, 1.6 times 10 to the negative 19th coulombs, and then multiply it by 1 volt, which is 1 joule per coulomb, you get 1.6 times 10 to the negative 19th joules. Okay, that's the amount of energy that a charged particle would acquire in accelerating through 1 volt of potential difference. Okay, so you could accelerate an electron through 1 volt of potential difference. It would have 1 eV of kinetic energy. Same thing with a proton. They would have the same amount of kinetic energy after being accelerated through 1 volt of potential difference. Okay. Moving on. So, you might remember from before we did this example problem where we calculated the electric field a small short distance above a plane of charge, an infinite plane of charge. And we also said that, well, if the plane of charge is really big and it's finite, but you're really, really, really close to the surface, you're like a centimeter away from a plane that's a meter on each side, it will look, for all practical purposes, it will look infinite to you. So if that is the case, then the electric field that comes off of this plane of charge will be equal to sigma, the charge per unit area, divided by 2 epsilon naught. Okay, so we did this example problem in chapter 21 when the hard way with the electric field calculations for continuous charge distributions. So this will matter for us quite a bit. So the first place that it matters is in terms of the capacitor. Okay, capacitors are really important. We're going to go in chapter 24, will be entirely about capacitors. But a capacitor has a charge plus Q on one side and minus Q, equal and opposite charge on the other side of it. There are 2 parallel plates, or sometimes there's 2 parallel cylinders. There's a bunch of different ways to make a capacitor, as we'll see later. But one of the interesting consequences of this equation here is that the electric field here, short distance from a plane, is independent of distance. So it's not like the electric field drops off if you move out here, right? So long as the infinite size approximation is good, the distance out that you go does not affect, the electric field does not drop off with distance. So one of the interesting consequences of that is if you take a capacitor like this, you will have, so you have a big plane of charge here, and you'll have an electric field extending out. Of course, on the other side of the plate, you'll have an electric field going in the other direction. Now, for a negative charge, right, electric field lines point towards negative charges and away from positive charges. So on the negative charged plate, you'll have electric field on each side. It will be pointing in, and each one will be independent of distance. So what that means is that the electric field, so if I use yellow to be the charge of the negative plate, or the electric field coming from the negative plate here, that means that we have an electric field going in towards the plate, and it doesn't depend on distance. So that means over here in this area, we also have an electric field that has the same strength as this one right here, pointing in towards the plate. And the red, so the positive plate here, sources an electric field over here that's in this direction as well. And the net result of this is that we have an electric field that cancels here, right? If you take these two things, this left pointing arrow and this right pointing arrow, and add them together, then you will have 0. Right? So the electric field is 0 in this regime here. And if you take this arrow here plus that arrow there, they will give you that the electric field is 0 in this regime here. And only in the middle here do the two things double up. So here you have the electric field from the positive plate and from the one sourced by the negative plate adding together. So you get 2 times this sigma over 2 epsilon naught, or epsilon inside the capacitor is sigma over epsilon naught. Okay, note that that's inside of the capacitor, right? Not inside of a metal or anything like that. It's the electric field inside of the capacitor. So outside of the capacitor it's 0, inside it's sigma over epsilon naught. Now let's talk about electric fields inside of conducting spheres. Okay, so in the electrostatic regime, and electrostatic just means that the charges have settled into their equilibrium positions. There's not currents flowing through either one of these conducting spheres here. The electric field inside a conductor then will be 0. Okay, and that's not just the case for conductive spheres, that's the case for any conductors. And this is one of those things that I'll repeat a lot, and it's really important, so make sure that you know that. The charge on a conductor always piles up on the edges, so there's no charge inside of a conductor. There's also no electric field inside of a conductor. And the reason why is pretty simple. It's just that if there was an electric field inside of a conductor, then since the charges inside of a conductor are free to move around, it would just flow out to, it would just flow in the direction that the electric field is pointing. For positive charges. For negative charges, it would flow in the opposite direction of the way the electric field is pointing until it made it to the surface, right? Once the charge gets to the surface, then it's not like it's easy for the charge to flow out of the conductor, right? It just is easy for it to flow within the bounds of the conductor. So, since like charges repel, if you put this net negative charge, right? If you put this net negative charge on a conductor, that negative charge will flow all the way out to the outside, right? So you'll get this pile up of negative charge that ends up on its surface. Inside, the electric field will be 0, and there will be no charge. Okay, here we have a conductive shell. Okay, so it's a 3-dimensional object. We are seeing a 2-dimensional slice of it. It's a conductive shell with a positive charge plus Q embedded in the center of it. So there's a plus Q right there at the center. Now, you know how this works. The charges in a conductor are free to move around, so if there's a positive Q charge that is at the center, the negative charges inside of the conductor will be attracted to it. They will pile up on the interior surface, and so you'll get a net negative Q charge piling up on the interior surface. And on the exterior surface, of course, the conductor has to be overall neutral. So on the exterior surface, you get a pileup of positive charge. So there's a plus Q on the exterior surface. Now, what we're going to do is use Gauss's law to find the electric field in the 3 regimes of interest. E1 interior to the shell, E2 within the conductive metal, and E3 out in the exterior beyond the edge. And we're going to call the interior R in, the interior of the shell, and the exterior R out. Okay, we can find all of these using Gauss's law. Okay, so here's Gauss's law. Let's get E1 first, okay? We can then use a Gaussian surface that will be, it'll be a spherical surface, right? Gaussian surfaces, the surface that you integrate over has to be entirely connected. It's got to be a 3D shape, always, as well. So if we integrate E dot dA surrounding this positive charge, well, we know that electric field lines point straight out from positive charges, and we know that so long as we choose our Gaussian surface properly, which we will, we'll choose it to be right with the positive charge right at the center there, then at every distance, so long at all points such that the distance is the same from that positive charge, the electric field will be pointing radially outward, and it will have the exact same magnitude, right? So dA is going to be, right, a little area element pointing out. dA is going to be pointing radially out, and the electric field E1 is also going to be pointing radially out at that point. So that E dot dA just becomes E times dA. Also, the electric field is going to be the same everywhere over the surface, so E is effectively a constant, right? It doesn't depend on which area element you're integrating over here. So we can pull out the electric field, E1, and then the integral over dA is just the surface area, A, of the Gaussian surface, which is just 2 pi r squared. And we'll set that equal to, according to Gauss's law, Q inside over epsilon naught. Well, what's the Q inside of this red sphere here? The Q inside of this red sphere is just whatever the magnitude of that point charge plus Q is, right? And then that's divided by epsilon naught. So we can divide both sides of this equation by 4 pi r squared, and we'll get that E1 is Q over 4 pi epsilon naught r squared, right? So you might remember that the Coulomb constant K here is just 1 over 4 pi epsilon naught. So what we found is that the electric field at distance r from a point charge is Q over r squared. So we already knew that. That's so there. That's our answer for E1. But we kind of already knew that one. But what's different about this is, just note, according to Gauss's law, the electric field, it only depends on Q inside of the surface. So even though there's there's all of this negative charge that's going to pile up on the inside of the conductor, on the inside of the conductive shell, that's not going to affect the electric field at all. Okay, let's talk about that charge that piles up on the inside of the conductive shell and the outside of the conductive shell. Okay, if the conductor is net neutral, and you stick this positive charge inside of the conducting shell, the negatively charged particles that make up the conductor are free to move anywhere, so they're going to be attracted to that positive charge. They're going to flow in towards the center there, which is why you get this net negative, right? This net negative over here that piles up on the inside of the conductor. But the overall charge of the conductor has to be neutral, right? So that just leaves us with a net positive charge on the outside of this conductive shell. Okay, so, but those charges, by Gauss's law, the electric field depends only on the Q inside of the surface. So those, that negative charge on the inside of the shell, the positive charge on the outside of the shell, has no effect on the electric field inside of the object. Okay, so that's interesting. Now, let's go on to E2. Okay, so we've gotten E1. I was using red for that. I'm going to use black for E2. Okay, E2 calculations are going to be in black. Now, E2, I'm going to use a Gaussian surface, right, that's inside of the conductive shell. Okay, and you'll note that I can take, so I'll apply Gauss's law right over here, and I will have that now the integral of E2 dA is going to be equal to Qn over epsilon naught. But what's the Q inside of this surface here? Well, this surface here, the interior of it encompasses both that positive charge in the center as well as the negative charge that has piled up on the inside. And the same amount of, so if this is a positive charge Q here at the center, you're going to get a minus Q total distributing itself evenly on the interior of this conductive shell. So the net charge enclosed by this surface is going to be 0. So the right-hand side of of Gauss's law is going to be 0 in this case, and that means that, of course, the electric field has to be 0, right? Because the area is not 0, so the electric field has to be 0. Inside of a conductor, the electric field is always 0, right? We can show that with Gauss's law and our knowledge that the charge piles up on the surfaces. Okay, what about E3 now? So E3, I will draw the surface in yellow, right? Of course, it has to be symmetric, but I can't draw very well, so it's not going to look that symmetric. Okay, E3 will use yellow for that. All right, so here, E3 dA is Qn over epsilon naught. Now note that this, the interior of this Gaussian surface encompasses the positive Q point charge. It encompasses the minus Q charge as well on the interior and the plus Q charge that will acquire on the outside of the conductive shell. So I get a plus Q, a minus Q, and a plus Q all inside of Q interior. So I end up then with Q over epsilon naught on the right-hand side, and I get the exact same thing on the left-hand side as I did for E1, right? On the left-hand side, I have an electric field times 4 pi r squared. So the electric field, E3, is KQ over r squared on the, for E3 outside of the conductor. Okay. So the electric field here inside of a conductor, of course, is 0. The electric field inside of a conductor is 0. The electric field near the surface of a conductor is something to think about. So let's say that we had an electric field extending out from a good conductor. Break it up into two components, all right? An E perpendicular to the surface and an E parallel to the surface. Okay. Now, we're in the electrostatic case, okay? So that means that the charges have all settled in their equilibrium position. So they're not moving anymore. Okay. Charges are free to move within a good conductor, but we're in the electrostatic case, so the charges are not moving. So the electric field that points in a direction that the charge could move if... let me try that again. The electric field that's pointing in the direction parallel to the surface must be 0. It has to be. If E parallel to the surface was non-zero, then the charge would move. It would move along E parallel, right? It would experience a force in a direction that it can go, parallel to the surface. So it would go that way. But we already said right from the outset that we're in the electrostatic case. So that means that it turns out that E parallel is 0. E parallel is 0 for the electrostatic case. Now, E perpendicular is non-zero. And that's important because, right, of course, there cannot be an electric field in this direction, because then we wouldn't be in an electrostatic case, the thing would move. There can be an electric field perpendicular to the surface because the charge is bounded to the surface. It can't just hop off. So it's fine, it's totally fine that E perpendicular is non-zero. So that's a good thing to know about the boundary conditions at conductors. So what this means is if I take a positive charge, let's do this in a different color. If I take a positive charge here, and I have a nice conductive surface here, this is a conductor. Let's just shorten it to cond. Okay, if I have a conductive surface here, and a positive charge there, well, the electric field lines that point out from a positive charge, they always point out from a positive charge. By the time these electric field lines make their way to the conductor, they have to be perpendicular to the surface. So, by the time they get here, they're going to have to be perpendicular to the surface. So in fact, what they'll look like is like this, right? This one's going to go straight there. This one's going to bend in. This one will bend in a little bit more. This one will bend in a little bit more, right? This one is going to bend in over here, right? So, and you know, this one's going to go all the way like out here and eventually make its way back over there. So the point here, right, is that if there's this positive charge there and there's a conductive surface there, there's going to be some negative charge that's going to pile up right at the surface of the conductor. The conductor is net neutral, but let's just say it has some kind of finite thickness here, right? The negative charges are going to be attracted to that thing. The positive charges are going to be repelled. So they're going to end up on this side. And that means that the electric field lines are going to go and point towards this conductor, right? But they're not going to point, point in any way that has a non-zero E perpendicular component to them, right? By the time you zoom in on the conductor, you would see that E parallel is going to be 0. It's pointing directly perpendicular to the surface at every point for the conductor. Okay, moving on. Now, here's a fun fact about electric fields and conductors. So, not only do when we look back at this thing that we had here, right? You put a charge plus Q in the middle. Minus Q acquires on the inside here, and positive Q acquires on the outside of the conductor there. And these pile up of charges on the interior and exterior serve to make it so that the electric field inside of the conductor, right, at this point, is going to be 0. But what's even cooler than that is that you can take an external electric field, let's say the electric field that's produced by this capacitor here, right, with this charge plus Q on this side, and it's this charge minus Q on this side over here. And this will be the source of this electric field. If you take a conductor that is hollow and shove it in there, then it will block out the electric field. The charge will redistribute itself on the surface of the conductor such that it will totally block out the electric field not only within the metal, but also on the interior there. So as long as there's no charge inside of the cavity in the conductor, there will be no electric field inside of the conductor. So this is really nice because sometimes extreme large amounts of electric charge, like say those generated by lightning storms, the thunder clouds up above, say acquire this very large amount of charge on the surface, right? There's ground down here, and these charges are piling up here, and they generate these very large electric fields pointing, up that way. And that makes these electrons want to jump down to the ground, right? That's called lightning. Now, if you could shield yourself inside of a metal cage or something, you wouldn't have to worry about being struck by lightning. So that's a pretty cool thing to know. If you're driving in a lightning storm and your car gets struck by lightning, don't get out of the car. This is that's actually a true statement. So I had to include this photo in here. I just love this picture. Look at this guy here. He looks so like from a terrible 1970s horror film or something. Look at this guy. He looks hilarious. He's inside of a metal cage. What is he doing? Anyway. So this guy's in some room where there's this very large electric field, and you can see, right, there's even, there's the air has reached what we call like breakdown, that electrons in the air could be accelerated by this external electric field. But this guy's inside of a conductive cage, so he doesn't have to worry about it. And so these electrons that are accelerated as shown on like the lightning on the screen here, he doesn't have to worry about it because he's inside of this conductive cage. All right, so you notice all those other slides that I had gone through were from chapter 21. Now this is a slide from chapter 22. Let's talk about then a little bit more about the electric fields near a conducting surface. Okay, so we have shown before that the electric field, we've shown you some things about the electric field surrounding near the surface of a conductor. Let's do this in the context of Gauss's law, doing a Gauss's law calculation with cylindrical symmetry. Okay. So this example asks us to show that the electric field just outside the surface of any good conductor of arbitrary shape is given by E equals sigma over epsilon naught. Now remember, sigma is Q over area. It's the charge per unit area. All right, let's do this. So I've already done it, but I lost all the audio. Okay. So I'm going to use a Gaussian surface. I want to find the electric field. I'm just going to pick out a point right here at some point, some short distance from the conductive surface. All right. In order to use Gauss's law, I need to integrate the electric field over some Gaussian surface. Okay. I drew my Gaussian surface as this cylinder here, just to exploit the symmetry of the problem. And you have to, if you want the Gaussian surface to serve you well, it better have the point that you're interested in on it somewhere, okay? And I am going to do this integral of E dot dA over this conductive surface, over this Gaussian surface given in red here. Now, I broke up the cylinder into three parts. S for the side, TC for the top cap, and BC for the bottom cap. So this integral here, right, remember this symbol, this circle in the middle just says around a closed surface, around the entirety of a closed surface. I can break this up into three separate parts. There is the bottom cap part, there is the top cap part, and there is the side part, right? So the bottom cap part has E dot dA, which is going to be 0. And the reason why is the bottom cap is located inside of a conductor, right? I've chosen this thing to straddle around the conducting surface. So the bottom cap is going to be inside of the conductor. It has the electric field there will be 0. So this term here is 0. Now, the electric field on the side is also going to be 0, but for a different reason. The reason is that the electric field near the surface of a conductor is always going to be perpendicular to the surface of the conductor. So if I zoom in on the side here, if I zoom in, right, I have electric fields. So here is my... Okay, here's my conductive surface. I'm going to zoom in on the sides, right, the sides here. Okay, the electric field emanating out from a conductive surface is always perpendicular to the side, right? Now, where is dA pointing for this particular Gaussian surface on the sides? Well, on the sides, dA is pointing outwards, right? I've chosen my Gaussian surface to exploit the symmetry of the problem, right? E dot dA is going to be 0, right? dA is pointing parallel to the surface, and the electric field has a 0 parallel component, so E dot dA on the sides is going to be 0. This part is going to be 0. On the top cap, E dot dA is not 0. That's the only non-zero term here. So going back and putting this into the equation, I can take E dot dA on the top cap, right?
on the top cap here, right, there dA is pointing up, right? So dA in that case is along the electric field, right? The electric field is also pointing up. Both the electric field and dA are normal to the conductive surface. So these two things are along each other. E dot dA is just E times dA because they're pointing in the exact same direction. That's equal to Qn over epsilon naught. The electric field is constant over the entire surface. So I can take E outside of the integral, and integral over dA across the top cap is just the area of the top cap. So I have E times the area of the top cap is equal to Q inside over epsilon naught, okay? And Q in here is the charge enclosed by this portion here, right? This portion here where the cylinder intersects with the conductive surface, right? All of the charge in here is included on the right-hand side in Q in, and the area here is exactly the same as the ATC, the area of the top cap up here. So I can divide both sides of this equation by ATC, and you'll see I have Q in over ATC. That's just sigma, Q over the area, right? So I end up with E equals sigma over epsilon naught, a distance from some conductive surface. Great. All right. So I would love to go through this other Gauss's law example 22-6, but I don't have time. However, you can look at example 22-6 on page 597 in your textbook. I would highly recommend that you do that. Okay, last one before I go to my final example, which is going to be a little bit longer. So here, the conceptual example is asking me, what is the, suppose that a conductor carries a net charge positive Q and contains a cavity, inside of which resides a point charge plus little q. What can you say about the charges on the inner and outer surfaces of the conductor? Well, here's what I can tell you. If I draw a Gaussian surface here, the electric field is got to be 0 because it's inside of a conductor, right? The electric flux has to be equal to Q inside of this surface over epsilon naught. Okay, and the electric flux through this thing where the electric field is 0 must be 0. So Q inside of this surface must be 0. So that must mean that minus Q acquires over this surface here, right? And if the conductor then carries a net charge positive Q, that means that this exterior here has to have not only the opposite plus little q, but it also must have that plus big Q, the net charge, because all the charge has to reside on either the interior surface or the exterior surface. And since the net charge on the conductor is positive Q, when I add the charge, the Q inside plus the Q outside on the outside surface, it has to be equal to plus Q, right?
Example of a Gauss's law problem with spherical symmetry. And the difference is that you're going to have an electric charge Q that is uniformly distributed throughout the non-conducting sphere. Okay, so this charge Q, so if this was a conductor, it's not. If it was a conductor, all of the charge would pile up on the edges. But it's not a conductor. Instead, we have some insulating thing. And in an insulator, you can distribute charges however you want. So in this case, they've they've chosen to distribute the charge throughout this sphere uniformly. So every little bit of the sphere has the same amount of charge on it. Okay, and we're asked to find the electric charge Q throughout this non-conducting sphere of radius r0. And so they want us to find the electric field A outside the sphere and B inside the sphere. All right, so let's do that. Get myself a little room here. All right, so A, we're going to find the electric field outside. Outside. Meaning at r greater than r0. Okay, so I'm gonna use the Gaussian surface A1 here, right, which is a sphere concentric with the center of this charge distribution. Okay, the electric field that comes out from this charge is going to be pointing radially outwards, and it's uniformly distributed, so there's a spherical symmetry there, which means that the electric field that's coming out from this thing is going to be spherically symmetric, right? That's true just by your knowledge of how symmetries work, right? If the charge is spherically symmetric inside here, then the electric field that emanates out from that source is going to be spherically symmetric as well. And so what that means is that the electric field is going to have to be pointing radially outwards. Right. So E is going to be pointing radially outwards, and that way, and that way. Okay, so E is entirely a radial component. Okay, I'm going to use r hat to be the unit vector that's pointing radially outwards from the center. Okay, then I can do, Gauss's law, E dot dA is equal to Q in over epsilon naught. Okay, the outside one is not too bad, right? What's the Q enclosed when you're at A1 there? What's the Q enclosed by that sphere A1? It's just the total charge Q. Right, the whole sphere is inside of the thing, right? So Q over epsilon naught is the right-hand side of this equation. On the left-hand side of this equation, right, dA is, of course, always pointing out normal to the surface. And E is also pointing radially outwards. So E and dA are along one another. So I can reduce this to EDA, right? And that's going to be equal to Q over epsilon naught. And, all right, you guys, can you hear me? Is this good? Just chime in if you can't. Okay. So EDA, right? The electric field, due to the symmetry, right, we're the same distance r away at every point along the sphere. So the electric field is going to be the same. That the electric field that's passing through each element dA over the surface is going to be the exact same. So you can pull E outside of this integral. So you will have an E integral over dA. And of course, integrating over the surface area just gives you the total surface area, 4 pi r squared. So here, now we're out to A1. And so this just gives you the exact same thing as what it would be if this was a conductive shell. Right? E is Q over 4 pi epsilon naught r squared. Cool. So it's the exact same on the outside of the sphere. That's not too bad. here, if I wanted to write this in vector form, right, I would put the r hat in there. What about B? B is the interesting case. So now my r is going to be less than r0, right? And I am, right, r is this distance out to here. So here we have r less than r0. Okay, in that case, just all of the arguments that I made about symmetries and stuff, talking about the left-hand side of the equation, all of that is equally true on the inside, right? E is along dA. The electric field is constant over the surface. It doesn't vary at different points across the surface. Left-hand side of the equation is exactly the same. I use LHS to refer to left-hand side. It's the same. Right? We still have E 4 pi r squared on the left-hand side. It's just that r is now smaller. On the right-hand side, we have something a little bit different, right? Q enclosed by the surface over epsilon naught. Now, what Q is enclosed by A2? Well, the amount of charge, the charge is uniformly distributed throughout the sphere. So what we could do is just say, well, Q enclosed is going to have to be equal to the amount of volume of this sphere that's enclosed divided by the total volume times the total charge. Okay? What we're saying is, since the charge Q is uniformly distributed throughout the volume, if we want the fraction of the charge that's enclosed by our surface in question here, what we can do is just take the fraction of the volume enclosed by that surface times the total charge Q. Fraction of the volume that's enclosed is going to be, right, so the volume of a sphere is 4/3 pi r squared. So the volume enclosed by our Gaussian surface here is 4/3 pi r squared. The total volume is 4/3 pi r0 squared. Right, so that's our volume ratio. And that's multiplied by Q. So, of course, this 4/3 pi cancels out on the top and bottom. Oh, sorry, did I write r squared? I meant r cubed. What am I thinking here? Okay. Volume. The volume of a sphere is 4/3 pi r cubed. You guys knew that. And so when I take this volume ratio, what I'm going to end up with is, since the 4/3 pi cancels out, Q times r to the third over r0 to the third. Okay. Putting this into the right-hand side of my equation, then, I have E times 4 pi r squared on the left-hand side equals Q over epsilon naught r to the third over r0 to the third. And I can cancel out this r squared on either. So r squared on this side will cancel out with this here, leaving this to be just a power of 1. And I'll have, then, dividing both sides by 4 pi, E equals Q over 4 pi epsilon naught times r over r0 to the third. Okay, so what this tells us is, right, the electric field right at the center of the sphere is going to be 0. And then it's going to increase linearly with radius out to the edge here. And once you get out to that point, it will then go into, you'll then be in regime A1, the A1 regime. So back up to this one here. And then it'll drop off like r squared. So if I wanted to draw a plot of this, where this is the axis r there, this is E here, and I have my sphere, say my sphere. Boy, that's one of the least spherical spheres that you could possibly imagine, but there you go. Let's just say it goes out to here. This is the point R0. If I wanted to plot E as a function of R, it would increase linearly up to R0. Once we get to R0, it would drop off like 1 over the distance squared. The same way that it drops off from a point charge, same way that it drops off from a conductive shell of charge Q once we're in the exterior regime. Okay, so here it would be proportional to R, and here it would be proportional to 1 over R squared. Okay, so that's the example problem that I wanted to do for you. And one thing that I should point out is just that's because sometimes people use this notation. We use this notation where rho is charge per unit volume, sigma is charge per unit area, and we also use lambda is a charge per unit length. So this is a useful thing to know, and it might be useful for you to, maybe look at some of the example problems in your text where you have a charge distributed throughout a unit length.